Hi everyone, today we are going to look at lessons 11.1 and 11.2. They are starting actually not necessarily in your book. I attached the notes handout sheet that you might want to follow along with just because I added an extra problem. But officially these are actually from your book or a notebook works as well, and then we'll move on to 11.2 being from your book. Now in the try these A section, when we talk about writing a polynomial of lowest degree, we want to look at the degree of the function and then our given zeros. So we know that the factored form here, if we write these zeros in factored form, we would have something like this, which we officially could condense a little bit further since we have that x minus 3 quantity squared because we've got that multiplicity of 2. This would work as a polynomial function of degree 3 with those zeros, right? And we could write this officially for letter B, same idea, x minus 1, x plus 1, x minus 3, x plus 3. Now you may also see this represented as conjugates because officially these are conjugates of each other, so we could actually just write this as x squared minus 1. These two are conjugates of each other, so x squared minus 9 would also work as well if we look at it that way. Now, officially, we can keep expanding these further as well because then it would be fully in standard form, which we'll talk about in a couple more problems. Now, we have to be careful with an example like part C because officially this is degree 3, but they're only giving us 2 zeros. And that's where we need to be careful with our complex zeros because we know they always come in pairs because of the complex conjugate theorem, right? So also negative 3i is a zero of this function. So that's where the degree 3 comes from, is remembering that we are going to also have plus 3i as an option. And again, when you expand this out, a reminder, if you need to, we're going to end up with, they are essentially conjugates of each other. So we end up with x squared minus 3i times 3i, which ends up being 9i squared. And then a reminder that I squared is really negative 1, so x squared plus 9, which makes sense when we think about when we get conjugates, the situations that we have those in. It would be when this is a plus sign because we would be taking the square root of a negative, okay? So just for expanding purposes. Now, again, we're just going to leave this here, not full standard form, but we'll talk about that a little bit later. Now, this next one, again, with our zeros, they're officially only giving us 3, but again, we know that 1 minus 2i also has to be a 0 due to that complex conjugate theorem. So we have x minus 1, x plus 3, and then x minus 1 plus 2i, and then x minus 1 minus 2i. So officially, when we simplify it, we have x minus 1 minus 2i. None of those can be combined. And then x minus 1 plus 2i. Officially, nothing can be condensed in there. Again, we can worry about fully simplifying this to standard form eventually, but as long as we're understanding the idea of zeros versus the factors, I'm good at this point. Now notice here, and this is for if we're going to expand it, so notice binomial theorem part. But if we want, we're only given the only zero is negative 4. We have no idea about complex zeros, but we want this to be a degree 5. Let's think about this thing having some multiplicity of degree 5. Okay, or you could write our f of x value, you could write x plus 4 times x plus 4 times x plus 4. You get the idea, 5 times, but we'll just leave it simplified like that for the sake of this problem. So again, relating the degree to our given zeros. Now here, we are just given a picture of a graph, and we don't necessarily know what the function is. We want to try and write an equation that mimics this. So some things that we want to be careful of here is identifying some features of our graph. So similar to what we had up above. We know that the degree minimum here has to be at least a 4. And the reason being there are 1, 2, 3 turning points. So that means that our degree minimum here, kind of like up above, is 4. Now our end behavior, we know our leading coefficient would have to be positive because of that end behavior. both opening upwards. And we want to identify these zeros because we officially have 3 of them, right? We have one at -3, 0, and 2. And we have to be careful about 0 because it's going to be a multiple root, right? It's got that maximum value at our graph here. So this is where we would have a multiplicity. So if we look at this like we were the other problems, f of x, we would have x minus 0, quantity squared, or just x squared, x plus 3, and x minus 2. So there's just our factored form of this, okay? Here's what I want to also talk about standard form. So this is our factored form. And again, we like factored form, a little bit less work. We could also expand this to standard form. So I'm going to start by doing that with expanding the x plus 3 and the x minus 2. If we double distribute, right, distribute the x through, we end up with x squared minus 2x. And then if we distribute the 3 through, we have plus 3x minus 6 when we multiply that through. And as we continue, we want to make sure we condense. And then we're actually going to need to, if we want full standard form, distribute through our x squared as well to get our final answer in standard form. So understand the difference between them asking you for factored form versus standard form going forward. Again, it's the same equation, just represented differently, okay? Now, that's all I really want to talk about with 11.1, and the ideas are going to carry into 11.2 as well, which is going to start in your books on page 146. Now, the first part of 11.2 is a lot of review. We're going to look at polynomials and factoring, and then we're going to talk about the forms. So this first part, just a reminder, anytime we have complex roots that are not factorable over rational numbers, but they might be factorable over real numbers versus factorable over complex numbers. We're talking about taking that square root of a positive number versus a negative number. That's what the lesson starts off as. And this just is kind of a review for us of being able to look at them, these graphs, set them equal to 0, find the zeros, real or complex. In this case, there were 2 complex zeros. And then they also want us to be able to write these as a product of linear factors. So there's a difference between finding the 0 and then writing it in its most completely factored form that we can. Okay, so that's what this example is here. We have a couple more examples down here, and I want to talk about letter B because it's similar to what we talked about above. And if you look for the 2 pieces, this first part wants us to find the zeros. So if we set it equal to 0, we're going to see that this is an example of having 2 complex zeros because we are taking the square root of a negative number. So that I has to move out front to show us that these are complex. So our 2 zeros are positive I square root 11 and negative I square root 11. If you then write this as a product of the complex numbers, we end up with x plus I square root of 11, and then x minus I square root of 11. So you'll see for this particular one, they wanted it written as a product of the complex factors. So you'll just leave it expanded like this, okay? Now part B then is asking us to, again, think about our being able to write these as a complex factors and zeros involving some factoring. So here, a reminder, treat these x to the 4th, x squared constant ones like we do our type 2. So they're kind of x method factoring what multiplies to be -14, adds to be -5, and solve through there, set each piece equal to 0. Again, when we talk about writing it in completely factored form, we're taking all 4 zeros here and writing them as individual factors and not leaving it as one simplified factor as we kind of were with the 11.1 stuff. And then again, identifying all of the zeros here, real and complex. So as we move on then to page 147, we'll see some more examples of this. So one of them I want to look at is letter C here. Scroll down a little bit. And again, it wants us to find all of the zeros and write it as complex factors. So for letter C, notice this is a factoring by grouping situation potentially. And we're going to want to look at what the greatest common factor is of each of these. So we have 2x minus 1 when we factor out the GCF of x squared in the first piece, and then our GCF in the second piece is 4, and we're left with the 2x minus 1 as well. So as we factor, we end up with 2x minus 1 and x squared plus 4. And as we set each piece equal to 0, we're going to get, again, a complex 0 situation where we end up with x being positive or negative 2i. And then over here, when we set 2x minus 1 equal to 0, x is going to be 1/2, right? And that's, again, showing 3 total zeros, which is good news for us. So when it asks you for your zeros, you can list your 3. So you have zeros at positive 2i, negative 2i, and positive 1/2. And then when they ask you to write it in a completely factored format, x minus 2i, x plus 2i, and then you could either say x minus 1/2 or just leave the 2x minus 1. Looks a little bit prettier, but either one works. Let's see. And then example D then is very simple to the one that in the given example, in that we can actually treat this as a type 1 factoring situation, this to the 4th squared, and then we have the constant. What multiplies to be 5, adds to be negative 6. Well, that's going to be negative 5 and negative 1 multiply to be positive 5, but add to be negative 6. So the only difference between how we normally do this is because when we have that to the 4th here, that means we're just going to treat these two terms as squared, and the rest will kind of work out. So as we set each of these two pieces equal to 0, we end up with a square root here of a positive value. So plus or minus square root 5. Same thing over here. When we set each piece equal to 0, plus or minus square root of 1, which is just 1. So our zeros, again, are 1, negative 1, square root of 5, negative square root of 5. And if we write this in factored form, we have x minus 1, x plus 1, x minus square root of 5, x plus square root of 5. Okay, so in this case, all 4 ended up being real zeros, no complex involved, and sometimes that'll happen. All right, last piece for today is we want to talk about the possibility that we don't have a nice factorable situation, as in when we talked about these sum or difference of cubes problem. Remember we talked about before that we just wanted to worry about this first piece here because that was the real 0. X equals 1 is our real 0. Well, over here, this wasn't factorable, right? So now we want to get this involved again, because what we're going to notice is using the quadratic formula, we're going to be able to find that these are going to be some complex zeros, again, using our pal, the quadratic formula. Okay, so let's look at a couple of examples of this. So let's look at part B together. And again, there's our quadratic formula. And this first part here, if we start factoring this, let's look at the fact that there is a greatest common factor between these of 3x squared to start. So we have x squared minus 2x plus 7 as a greatest common factor factored out, and we're left with that. Now, we know that if we set this 3x squared equal to 0, 0 is going to be one of our zeros. Unfortunately, for the second part, there's nothing that multiplies to be 7 that adds to be negative 2, because the only factors of 7 are 1 and 7. There's no combination of that that's going to equal negative 2, so it's not factorable. So this is where that quadratic formula is going to come into play, because we're going to have x equals negative b, so positive 2 now, plus or minus the square root of b squared, so negative 2 squared is 4, minus 4 times A times C all over 2A, which is 1 here, okay? Now, if we start simplifying this, we end up with 2 plus or minus 4 minus 4 times 7, which is 28, is going to be negative 24. And then I'll divide it by 2. And then officially, we can simplify this to be 4 times 6, aka that perfect square of 4 will move out, and it becomes the square root of 4, which is just 2. And then because of that negative, this is officially an I. So from here, we're left with 2 plus or minus 2I square root 6 all over 2. And then that 2 in the denominator can cancel with both pieces of this, so that we have 1 plus or minus square root of 6. I is still out front here. So our 2 zeros here, besides the x equals 0 that we have before, we have x equals 0, 1 plus I square root 6, and 1 minus I square root 6. Now, the other example here is a little bit nicer in that we don't have any GCFs to worry about, but we do want to worry about here the factoring. So again, if we plug into the quadratic formula, we end up with negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. And we have negative 3 plus or minus, and then 9 minus 44 is negative 35 over 2. Now this one does not work out as nicely. The 35 does not break down nicely. So really all that we're left with here is that we can move out the I to get rid of that negative under the radical, but this does not simplify into anything pretty. So really our only 2 zeros here for part A are negative 3 plus I square root 35 divided by 2, or negative 3 minus I square root 35 divided by 2. And sometimes you'll see that broken into 2 fractions. You can leave it as 1 fraction though, I'm okay with, okay? We are going to skip part D and talking about that, so we'll not worry so much about that. And then we'll move on then to these lovely check your understanding questions. So answer here. And then we will work more with these 2 lessons in class. Thanks, everyone.